linear function pattern recognition, we're going to continue to identify rates of changes from a table and finding missing values from a table or extending that table in either direction using what we know about rate of change. So for each table below, fill in the blanks if necessary and identify the rate of change, the unit rate, and identify the type of function represented by the table. So the first thing we do whenever we're looking at a table is to find the change in X and the change in Y. In this first table, you'll see that we're not missing any spots in our table. We don't have to fill in any blanks, so you just are going to do the change in X and the change in Y. So when I'm looking at my number line, if I'm at -2 right here and I need to go to +2, I'm going to the right from -2 to 2, and I'm going to the right 4 units. So that's increasing by 4. You're going to want to continue to do this down the table. When I look at my table now, you can see that I have varied changes in X, 4, 1, 4, 3, 5, 3. We have different values here. And I have varied changes in Y. What does that mean in terms of my function type? You can still find the rate of change, and you're going to need to find the rate of change for each one of these pairs. So we're going to find the rate of change for this change in Y and change in X. We're going to find the rate of change for this, and so on. We're going to find the rate of change for every different pairing of change in Y and change in X to see, is this a linear function? Because in order for a function to be linear, it has to have a constant rate of change. And just looking at this, it doesn't look the same, but it may still be constant. So I pulled a little sticky note over here to give myself a little bit more room to write. You can do this in your margin. So rate of change is the change in Y over the change in X. I just set that up here so you can see that. So for my first one, you can see that's right here. My change of Y is 12 and my change in X is 4. I'm going to write that over in my sticky note. You can put that in your margin. So I have positive 12 for my change in Y, and my change in X is 4. That can be reduced to a unit rate. It can be divided out, and 12 divided by 4 is 3/1. That's my unit rate. It divides evenly. Let's take a look at my next one, and you can see right here that my change in Y is 3 and my change in X is 1. That's already a unit rate, but let me write that down so that we see that. So my change in Y is 3 and my change in X is 1. So far, I have constant rate of change because I can see that this 3/1, 12/4 reduced to 3/1, which is the same as what I had here. Let's take a look at the next different one. I'm skipping this one right here of 12 and 4 because I already did that up at the top, and we know that it would be the same. So now I have a change in Y, which is 9, and a change in X, which is 3. And you can see that that reduces again. 9/3 has a unit rate because 3 divides into 9 3 times. Let's make that look a little neater, to be 3/1. Let's take a look at this last one, or the last different one, I should say. So here I have 5 is the change in X and 15 is the change in Y right here. We're going to write that in its unit, in its rate of change form. And again, 5 divides evenly into 15. 5 goes into 15 3 times. So this also reduces to 3/1. So now you can see that each of our fractions has the same unit rate of 3/1. This last one here that we didn't do out is the same as 1, 2 above. So 9/3 is going to be just like it is right here. So I'm not going to write that a second time. So all of these fractions reduce to the same unit rate. You can write them as equivalent fractions here with the unit rate as 3/1. So this is how I would summarize this, and I would just write each of the different rates of change, and that they're all equivalent, and they're all reduced to 3/1, which is my unit rate that I have written right here. And of course, if they can all be reduced to a constant unit rate, so this is constant, we should write that in right here. We have a constant unit rate because it can be reduced to the same or we have a constant rate of change because it can be reduced to the same unit rate, and so that means our function is linear. Now we're going to take a look at question 2, and again, we're going to always start with the same thing, which is to do the change in x and the change in y. So in looking at my changes in x and my changes in y, I can see they're different again. That does not mean that this is not a linear function. We have to do the rate of change to know that. We need to know if it reduces to a constant value, to a same value. So for this table, we have two different rates of change that we have to identify. We have negative 15 over 3 and negative 20 over 5. And hopefully we see that these fractions, 3 divides into 15 evenly and 4 divides into 20 evenly, and they both turn out to be negative 5 over 1. So they are equivalent because these are equivalent to negative 5 over 1. That's our unit rate. Those are equivalent fractions because 3 goes into negative 15 negative 5 times, and 4 goes into negative 20 negative 5 times. So because this is a constant, and you want to write this down, because this is a constant rate of change for the whole table, this is a linear function. For this last table, we have some missing pieces. So we are going to do what we did before, which is find the change in x and change in y, but we're going to have to use this information in order to fill in some of these blank spaces that we see in our table. So we can find the change in x for every single one of these values. We cannot find the change in y for every single one of these values. We need to focus on the ones that we have between. So we're going to look between 52 and 36. And then we're going to go from 36, and I'm making this big because we'll eventually want to know the gaps between the parts that make up this. But we can find the difference between 36 and 4, as well as between 4 and negative 20. In looking at this table, hopefully you see here from negative 8 to negative 4 is increasing by 4. Remember, you can look on your number line. From negative 8 to 4, you're going to the right to get there. That is in the positive direction. From negative 4 to negative 1, again, you can use this number line to see which direction you're going and by how many spaces. So we see these different values here. For the y's, we could only do these ones that I drew in green, which these don't totally correspond to everything we see in the change in x's. So like this right here is one connection that we can make, but this 32 is actually more spaces. So what I would do is look at that's going from here to here. And so you can do that by adding the 3 and the 5 that you see here, or you could just go back to the number line and look at negative 4 going to positive 4. And that's going to the right, and you could count those spaces, and that is increasing by 8. But you could also get that by adding the plus 3 and the plus 5. So here we have another relationship of 32, negative 32, and positive 8. And then we need to do the same thing for this negative 24 is the difference between 4 and negative 20. So if you're over here at 4, and you have to go way over off the graph, you're going to the left. That's why it's negative. So from 4 to negative 20 is negative 24. So you also have to look, so that's grouping here. The difference between 4 and 10 is increasing by 6. And so we have to look at that relationship between the negative 24 and the positive 6. So when we look at these rates of change, negative 16 divided by 4 is negative 4 over 1. Negative 32 divided by 8 is also negative 4 over 1. And negative 24 divided by 6 is also negative 4 over 1. So these are equivalent rates of change. That is another way of saying they're a constant, which means that the function is linear. Now, how do we fill in those missing pieces? Come in here and look. And so one of the things we need to find is, what is this piece that's right here? And we know from -4 to -1 is increasing by 3. So that tells us the proportion. So think of what our rate of change tells us. When it's -16/4, that tells us that as y decreases by 16, x increases by 4. You could say that in the reverse. As x increases by 4, y decreases by 16. Now, that's not what we have. We have 3. None of these are 3. So we could think of doing our table using our rate of change. And we could go by 1. We could imagine that we are putting in extra spaces in here, and we would need to put in 3 spaces. So there's a couple ways you can think about it. You can literally think about expanding your table. This is not something you have to have written down, but I just zoomed in and popped in a little Post-it here to kind of look at what would happen if I expanded this table from here to here. So in the Post-it that I have, I basically put this table, but instead of going by 3 and by 5 for the x, I went by 1s. And you can see that right here that from -4 to -3 is increasing by 1. Each one of these is increasing by 1. And so we know from our unit rate that if the x increases by 1, that's right, that's what we're saying right here, that the y is decreasing by 4. So as my x increases by 1, as I see in this pop-out table, then my y should be decreasing by 4. So 36 minus 4 is 32. 32 minus 4 is 28. So looking at all of these y values, if you decrease by 4 for each one of those, I end up right here at 4, 4, which is at the end of the table. So decreasing by 4 works. What we need for our table is actually what happens here at -1, which is there in the table. And so at -1, if x is -1, y is 24. Another way to think of this is to look at this change right here. So this is x is increasing by 3. And so we need to do 3 times whatever your unit rate is. So our unit rate is right here at -4. So it's got to change by 3 times -4, which is -12. So I need to take 36 and subtract 12, which is 24. So to finish up our table, I can see from -1 to 4 is increasing by 5, like I had here in my table. So that's 5 times the unit rate, because in our unit rate, we're looking at what happens when x increases by 1. Now x is increasing by 5. So this right here is going to be 5 times the -4. So I'm supposed to increase by -4, but I need to do that 5 times, which is -20. So 24 minus 20 is 4. That's what I have there. So to fill in this next blank, from 4 to 8 is increasing by 4. So I need to go 4 -4s, or 4 times -4, which is -16. So 4 minus 16. So I'm going to the left. So from 4 to 0 is 4, and I need to go 12 more. So that is going to be -12. Again, look at your number line to help you with that. You can count that down. And then the last step here, the x's are increasing by 10, which means I need to 10 times decrease by 4, or 10 times -4, which is -40. So -20 minus 40 is actually -60 to end there. In summary, we continue to talk about rate of change in terms of change in y over change in x, and that the unit rate is always something over 1, and it's that dividing out your change in y over change in x over 1. Linear functions are always have a constant rate of change in the same unit rate, and this is the key thing for this particular unit. Jumps don't need to be the same for a function to be linear. If you check the rate of change and it all reduces to the same unit rate, you know it is still a linear function. Your notes should look like my notes. You should have your changes of y and changes in x, as well as showing that all of the rates of change are equivalent.